Good morning, my name is Johan Mortara, and today I am presenting you the latest improvements that we made on the symfinder toolchain to increase its capabilities in identifying variability implementations in a single object-oriented codebase. But first, let me introduce you about the main concepts behind symfinder. We all know huge variability-rich systems, and because of their important size, managing their variability is a difficult task. We would like to be able to master their variability as in the software product line, but this implies being able to identify variability implementations in the codebase to then be able to map them to domain features. We already know some techniques that help us in doing that, for example, in projects using a clone and own approach to manage their variability. However, object-oriented software systems are able to manage their variability in a single codebase, using the mechanisms provided by the language, which are therefore the same ones used to implement the code assets, so identifying them is not trivial. To reach this goal, we developed an approach relying on the notion of local symmetry to identify variability implementations in object-oriented code assets. Symmetries are present in object-oriented mechanisms, such as inheritance, method and constructor overloading, and design patterns, as they all exhibit common and variable parts. You can find more information about this notion of symmetry in this paper, which has been published last year at SPLC. Once these symmetries have been identified, they are displayed using a graph visualization, which is not symmetric itself, but exhibits for each class the different symmetries it possesses. For example, the inheritance relationships between a superclass and its subclasses are the edges of the graph, and the method-level symmetries are shown using different properties of the nodes, such as their color or their size. By detecting symmetries, we are able to identify variability implementations. Hence, a high density of symmetries in some place of the code implies a variability-intense place. But what exactly is the notion of symmetry? Let me show you on an example. FreeChart is a 2D chart library written in Java, which allows one to draw different types of charts, such as pie charts or line charts, for example. These different types of charts represent domain variability that we expect to identify in this codebase. Same goes for the different time units that are also used in some charts, such as the chart shown here. Let's see if symfinder is able to identify these variability implementations. This visualization has been generated by symfinder after analyzing a single version of FreeChart. We can see on the visualization the presence of multiple trees made by nodes linked together, such as this one, or these two ones here. These zones are dense in symmetries, therefore variability intense, and are likely to implement domain features. If we zoom on this zone here, we can see a variation point which is called plot, which has for variants in subclasses being XY plot, category plot, or pie plot, and other ones. This variation point implements the behavior which is common to all the types of charts we can draw, whereas the variants implement the behavior specific to each one. The same goes for this other zone here, with a variation point called regular time period and its variants, month, year, etc., which represent the implementation of the different time units. Knowing which code assets are implementing a feature is important, but knowing how these code assets interact in the codebase is also important. As features are often grouped in packages, we added an option this year on symfinder's visualization to be able to color variation points belonging to a given package. For each package entered, symfinder will pick a color and use it for all nodes representing classes belonging to this package. Now let's open the box to see how symfinder works inside. In its first version, symfinder took as input a single Java codebase hosted on the Git repository, identified the symmetries relying on a graph representation of the codebase, and provided a visualization of these symmetries under a graph visualization. The whole toolchain is fully Dockerized, and running it at the project is really simple. After specifying the different information on the project in a YAML file, running symfinder is as simple as running a shell script with the project's name in parameter. A detailed guide on how to run symfinder is available on its GitHub repository. I leave symfinder running for the moment, we'll get back to it a little bit later. One of the first improvements we made to symfinder this year is to add another parser for C++ code bases. C++ code is likely to contain macros that may introduce variability, so we need to expand them to visualize all the variability implementations. In case of a C++ project, symfinder will first preprocess the sources by extracting CPP macro definitions and replace their usages by their definition during the preprocessing phase. However, we do not identify the variants that are potentially created by these directives, but this is part of our future work. The other parts of the toolchain remain unchanged, and the generated visualization of a C++ project is similar to the one of a Java project that I have just shown you. Let's see an example of C++ project together. MuseScore is a free music notation and composition software written in C++. And as for FreeChart, we expect to identify some domain variability. Here, the elements that compose a music sheet are of different types. There are some musical elements, such as the key, the time signature, the tempo, or the wedges, and also some textual elements, for example, the instrument name or the measure numbers. Let's see if symfinder is able to record this information. We can observe that the visualization of MuseScore exhibits less trees than the visualization of FreeChart. This can mean that MuseScore is less variable than FreeChart, but it can also mean that the domain features are implemented in variants which are not variation points. For such cases, we added a button on symfinder's visualization to be able to display all variants. Multiple trees appeared, such as this one here, whose variation point is called music data, and which has for variants tempo, key, measure repeat, or wedge. These hence represent the different musical elements of a music sheet, whereas the textual elements of the music sheet are represented here on another dense zone. Once again, symfinder is able to record this information. Domain features are sometimes annotated in the code sets, and these traces are valuable for variability identification. When such information are available, symfinder is able to map these traces to the identified variation points and variants. By specifying in symfinder's configuration file the path of the files containing the traces, scripts will read them and use symfinder's textual output to map them to the variation points and variants and calculate precision and recall measures. Mapped variation points and variants will appear with a blue border on the visualization. One such project with existing traces is Argo UML SPL, which is a software product line extracted from Argo UML and a well-known case study for feature identification and feature location techniques. The codesets have been annotated, and traces from the features to the codesets implementing them have been extracted. The identified features correspond to the different types of UML diagrams that can be drawn using Argo UML. Let's have a look at the results of the mapping between these traces and the variation points and variants identified by symfinder. Symfinder has finished analyzing Argo UML. After having identified variation points and variants, they are mapped automatically to the traces, and precision and recall measures are calculated. Let's have a look at the generated visualization. Let's show all the variants to show other trees on the visualization. On this visualization, all the mapped classes have a blue border on the node. By looking at this particular variation point and its variants, we see that each variant is mapped to a trace of a different feature. This means that the variation point implements a behavior which is common to every UML diagram, and each variant implements the part which is specific to every diagram. We can also suggest that the variants that have not been mapped may be codesets implementing features which were missed during the extraction of the software product line. The visualization for all projects are available online on the live demo page of symfinder. You can also obtain symfinder on its GitHub repository and run it on your own project. Please do not hesitate to keep us informed of the results that you obtain by running it on your own project. We would really be happy to hear about it. Thanks for your attention.